The torque on a gate in a dam. The upper edge of a gate in a dam runs along the water surface. So this is the surface of the water which is aligned with the upper edge. The gate is h equals 2 meters high and w equals 4 meters wide and is hinged along a horizontal line through its center. So this is the hinge, therefore this can rotate like this if there is enough torque. Calculate the torque about the hinge arising from the force due to the water. So this water exerts a force on this portion and therefore it's going to apply a torque as well. So if we set up our coordinate axes here, you can see that we have this x-axis, y-axis and z-axis. And this is the height h, this is the width w, the hinge is right here. If we are at a distance y from the origin on the y-axis, we are at a distance h minus phi from the upper surface. So symmetrically with respect to this hinge, we have water on top and water at the bottom. So there will be a force due to the water on top of the hinge, and that force will be in the plus k hat direction. And the water below the hinge will also be applying a force in the plus k hat direction. And if I take an incremental portion here with dy, you can see that this force will be applied. The force that will be applied will be equal to dF. So my observation is that the water in the dam exerts a force per area in the plus d direction on a strip with w height dy located at a distance h minus y from the surface. So y from the origin, h minus y from the surface. It has a width dy and there is a force dF applied on it. Okay, now how does the pressure vary with y? Well, we have the outside pressure P0, and then when we go into the water to a distance h minus y, there will be rho g h minus y additional pressure at the level of this segment. And on the other side of the dam, of course, we have air pressure as well. So air pressure here, air pressure on this side, and rho g h minus y on this side. Okay, so if I write this here, the pressure varies as a function of y, P0 atmospheric pressure at the surface of the water plus rho g h minus y at a distance h minus y from the surface, y from the origin. And on the other side of the dam, I also have atmospheric pressure, so that the pressure varies as a function of y, rho g h minus y. Now, what is the force exerted on this segment? dF as a function of y. It will be equal to the pressure at that point multiplied with the area of the segment, which is w times dy. So I will find that the force is rho g h minus y w dy. Okay, now I'm going to start considering the torque. So what is the torque due to the in the upper portion as a function of y due to the water? Now, if I'm at a distance h minus y from the surface here, you can see that since this segment has a total depth of h over 2, because this is at the center, this is at a distance y minus h over 2 from the middle line here, which is the hinge. Okay, so I'm at a perpendicular distance y minus h over 2 from this segment, and there is this force dF up which is being applied. So R cross F, so I go from the hinge towards the point of application of the force, R cross F with the right hand, 4 fingers point in plus j hat direction. I curl them towards k hat direction. The thumb points to the right. So this has a rotational effect, which is in this direction, which is in the clockwise direction. But according to my setup here, that produces a torque in plus I hat direction. Okay, so with those observations, I see that I have a distance r, y minus h over 2, the force dfy, and the angle between these is 90 degrees because they're perpendicular to each other. So if I calculate the net torque in the upper portion of this part of the dam, it will be an integral from h over 2 to h. So y goes from h over 2 to h, so that I will be covering the upper portion here. It's the perpendicular distance y minus h over 2 multiplied with the force rho g h minus y, pressure multiplied with the area w dy, and with the right hand rule I have found that it is in r hat direction. So remember, torque is r cross f. Okay, so let's start taking this integral. The torque in the upper portion will be, so if I take this into rho g w parentheses, the integral from h over 2 to h. So if I distribute this, I see that I have h times y, the first term. Then I will have minus h squared over 2, this second term, h squared over 2. The third term is minus y squared, so that's the product of these two, minus y squared. And then the fourth term will be equal to h times y over 2, so the product of these two, so that is plus hy over 2 dy in I hat direction. So you see that I have hy and hy over 2 here, so let's add them up. So this will be rho g w integral from h over 2 to h. Hy plus hy over 2 is 3hy over 2. And then I have minus y squared, and then I have minus h squared over 2, and dy in I hat direction. All right, so let's continue. The torque due to the upper portion is rho gw. If I perform this integration now, from the 3hy over 2 term, I will get y squared over 2. So this will be 3h over 2 multiplied with y squared over 2. And this term will give me y cubed over 3. So I will have minus y cubed over 3, the integral. And then from minus h squared over 2, I will have minus h squared over 2 multiplied with y. That's the integral. And this will be evaluated between h over 2 and h and multiplied with I hat. It's in the I hat direction. So this can be rewritten as rho g w. Now I have 3h over 4 y squared minus 1 over 3 y cubed minus h squared over 2 y evaluated between h over 2 and h in I hat direction. All right, so the torque in the upper portion is, now I will start evaluating. So evaluated at h, I'm going to get an h square here, so this will make it h cube. So I will have 3h cube over 4. And then for minus 1 over 3y cube term, I will have minus h cube over 3. And then minus h squared over 2y term becomes minus h cube over 2. That's when it is evaluated at h, minus evaluated at h over 2. So minus, now I put h over 2 for y squared. I'm going to get 3h over 4 multiplied by h squared over 4. H squared over 4 minus 1 over 3 y cube, which is h cube over 8. H cube over 8. And then I will have minus h squared over 2 multiplied with h over 2. And this is in the I hat direction. Okay, so this gives me rho g w, and I have 2 over 4 h cube here, 3 over 4 h cube here, so this gives me h cube over 4. And then I have minus h cube over 3 minus, so the first term here is 3 over 16 h cube, 3 h cube over 16. Then I have minus h cube over 3 times 8, 24. And then I have minus h cube over 4. So the last term is h cube over 4. This is in I hat direction. Okay, this is basically equal to rho g w. So if I make this into the common denominator, in order to make the common denominator 48, so this will be rho GW divided by 48. Rho GW divided by 48. I see that I have here 12 times 4 is 48, so this will be 12h cube over 48, so this is 12h cube. And 16 times 3 is 48, so this is minus 16h cube. And then here I have 9h cube, but there's the minus sign, so this will be minus 9h cube. 24, so this should be multiplied by 2, minus 2, minus minus becomes plus. So this is plus 2h cube. And then I have 12 multiplied with 4 is 48, so this will be 12, but minus minus becomes plus, so this is plus 12h cube in I hat direction, and that gives me in total, if I sum it up, you can see here 12 plus 12 is 24, plus 2 is 26, 16 plus 9 is 25, 26 minus 25 gives me 1. So this will be equal to rho GW over 48 h cube in I hat direction. Okay, so that's the upper portion. Now let's start working on the lower portion, the torque low. This will be a similar calculation. Now, what is the perpendicular distance for the lower portion? So here I'm at a distance y. from the origin of this coordinate system on the y-axis. And now my distance with respect to the hinge is h over 2 minus y. So h over 2 minus y, but the force is in the same direction. So I can say that I'm at h over 2 minus y. That's the perpendicular distance. The force dFy and sine of the angle between them is 90 degrees. So that gives me the torque for the lower portion is the integral from 0 to h over 2. Now perpendicular distance h over 2 minus y, rho g h minus y, that's the pressure multiplied with the area of the segment w dy, and now it's in minus I hat direction. Let's see that. I go to the point of application of the force from the hinge, so it's in the minus j hat direction with my forefingers. I curl my forefingers towards the application direction of the force, which is plus k hat direction, and I see that the thumb points in minus I hat direction. Okay, so that's the integral I should perform. So the torque for the lower portion is rho g w. Now it's basically this one was y minus h over 2 times h minus y. This is h over 2 minus y times h minus y. So it's going to be the same thing, except the first term here will be h squared over 2, so this will become plus, and then I will have minus hy over 2, so this will become plus, this will become minus hy, and this will be minus, and this will be plus y squared. And here I have this minus I hat. So if I operate this minus sign here, this actually becomes y minus h over 2, the same thing as this one. So therefore, I can use actually this result here, the same result that I have obtained here when I performed this integral. Okay, so because of this minus sign making this y minus h over 2 exactly the same as the top one. So using the result obtained there, I have 3h over 2 y squared over 2 when I performed the integral. Then I have minus y cubed over 3. Then I have minus h squared y over 2. Exactly the same result, 0 to h over 2 in plus I hat direction. So let's check. This was, that's the result obtained here. 3hy over 4, hy squared over 4 minus 1/3 y cubed minus h squared y over 2. So I've copied that result here, but it will be evaluated between 0 and h over 2. Now this becomes rho g w. Now when I evaluate it at h over 2, you see this becomes h squared over 4 multiplied with 4, it becomes 16. So this is going to be 3h cubed over 16. And when I put h over 2 here, this becomes h cubed over 8 multiplied by 2 is 24 minus h cubed over 24. And h over 2 here makes this h cubed over 4. So this becomes minus h cubed over 4 in I hat direction, which is rho g w. So if I take this into 48 common denominator, then the first term I will have here is 9h cubed, because I have to multiply it by 3, 9h cubed over 48. Then I have minus 2h cubed, because of 24 I have to multiply it by 2. And then I have minus 12h cubed multiplied by 12 because of this 4 in order to write the common denominator here in plus I hat direction. And the result will be, for the lower portion, 9 minus 14 minus 5 over 48 minus 5 over 48 rho GW h cube in I hat direction. Now we're ready to calculate the net torque. The net torque is plus 1 over 48 in I hat direction and 5 over 48 in minus I hat direction, rho G W h cube I hat. Therefore, I see that the net torque here will be, minus rho GW h cube over 12 in I hat direction. 4 over 48, that is 12. So that is my symbolic answer. If I substitute the numbers for the net torque, I will find minus rho density of water is 1000 kilograms per meter cube, G is 9.8 meters per second square, W is 4 meters, H was 2, its cube is 8, divided by 12 in I hat direction, and this gives me a net torque in to be minus 2.61 times 10 to 4 Newton per meter I hat. So it's in minus I hat direction. Does that make sense? Because the pressure increases when I go below this surface, and that's going to apply R cross F a torque in the counterclockwise direction, and because this force is larger on this side than this side, the lower portion will win in this situation. Okay, so we talked about the torque on a gate in a dam. The gate is 4 meters wide, 2 meters high. It is hinged along its central line, and we want to calculate the net torque on this gate. So we look at the upper portion and lower portion separately. So the upper portion, we have y minus h over 2 distance with respect to the hinge, and in the lower portion, h over 2 minus y distance, because y is less than h over 2 in this case. And each of these segments that I consider here have a width dy. Okay, so at a distance y from the origin, and with dy, so on the y-axis. All right, so if I look at the direction of the torque, so it's R cross F here, I see that the torque due to the upper portion is in plus I hat direction, and R cross F gives me a minus I hat torque, so they will be pointing in opposite directions. And the pressure as a function of y varies so we have the atmospheric pressure on top of the water surface, atmospheric pressure on the other side of the gate, and then we have rho g h minus y. H minus y is the distance with respect to the surface. That's the pressure multiplied by the width of the segment I consider, w dy, and also the height. So this gives me the area multiplied by pressure. That's the force as a function of y. The torque for the upper portion, as I said, is y minus h over 2 df sine 90. This has to be integrated between h over 2 to h, that's the upper portion, and that gives me an answer, rho gw over 48 h cube I hat. For the lower portion, it is in between, the distance is h over 2 minus y. It is in between 0 to h over 2 in minus I hat direction. I noticed here, if I operate this minus sign, it's identical integral. So that's what I did here. And as I thought the torque turned out to be in minus I hat direction from this calculation. The net torque with the torque due to the lower portion being higher is minus 4 over 48, which is minus 1 over 12 rho GW h cube I hat. We can substitute the numbers to get the numerical result.